Today, we're diving into the secret engine hidden inside every single tree. It's this silent, incredibly powerful force that lifts water to the very top of the tallest giants on Earth. I mean, really think about it for a second. How does a massive tree, some of them 300 feet tall, get hundreds of gallons of water from its roots way down in the ground to its very highest leaves? Every single day. There's no heart, no pump. It seems to defy physics. Well, that's the exact mystery we're going to solve today. And to figure it out, we're going to follow the data. We're going to watch a single tree over a 24-hour period to see exactly when it gets thirsty and, more importantly, how it gets its drink. Okay, so this graph right here has all the clues we need. It's tracking two really important things. That solid line, that's transpiration, which is basically just water leading the tree from its leaves. And the dashed line, that's stem flow, which is the water moving up the trunk from the roots. Got it? Let's move on. So let's trace the story these two lines are telling us. We'll start our day with the tree. If you look at the bottom axis, around 4 a.m., everything's quiet. The tree is kind of just sleeping. But then the sun comes up. And when that sun comes up, it's like someone turns the key on the tree's secret engine. An engine that, doesn't run on gasoline, but on sunlight and water. And this engine has a name. It's called transpiration. So what is transpiration? Well, it's really just the process of water evaporating from a plant's leaves. As the sun warms them up, water turns into vapor and escapes through these tiny little pores. You can almost think of it as the tree sweating. But here's the thing, it's not just a side effect. This sweating is the engine. It's what powers the entire water transport system. And the more sun you have, the faster that engine runs. Now, let's connect that back to our graph. See that solid line? Right after sunrise, around 6 a.m., look at it, it just shoots upward, and it hits its peak mid-morning. That is the transpiration engine revving up as the sun gets stronger. The tree is losing a lot of water. Okay, so the tree is losing water from its leaves. Fine. But how does that help get water up from the roots? This brings us to the most important, and maybe the most surprising, piece of this whole puzzle. So here is the multi-million-dollar question. What actually happens first? Does the tree push water up from its roots, which then causes it to evaporate? Or does the evaporation from the leaves happen first and that actually pulls the water up? Push or pull? The graph gives us a crystal clear answer. Look closely. The solid line, transpiration, the pull, it peaks around 10 in the morning. But the dashed line, the actual flow of water in the stem, that doesn't peak until afternoon. There's a really obvious time lag. And that, right there, is the big secret. The pull from the leaves always comes first. A tree doesn't push water up from its roots, it pulls it. That evaporation at the top creates a tension that literally yanks columns of water all the way up from the ground. And this isn't some weird one-off thing. Check out this data from a completely different plant. It shows the exact same relationship. The dashed line, transpiration, it peaks first. Then, hours later, the solid line, which is the water coming in from the roots, it follows. The pull always dictates the flow. Okay, but what is this pull? I mean, it's not a tiny rope and pulley system, right? No, it's actually a really powerful physical force. And to understand it, we need to talk about the physics of being thirsty. So let's look at graph 2, our second piece of evidence here. This measures something called leaf water potential. Now notice how right as transpiration in that first graph is peaking, this line absolutely plunges. It goes super negative. That drop right there, that represents a massive suction force being created inside the leaves. So what on earth is water potential? Just think of it like this. It's a way to measure how much water wants to move. And there's only one rule you need to remember. Water always moves from an area of high potential to an area of low potential. It's just like a ball rolling downhill. It's that simple. Now, I know that can sound a little abstract, so let's make it super concrete. All we need is a peeled grape. So if you take a peeled grape and you put it in a glass of pure water, which has a very high water potential, water flows into the grape, and the grape actually gets heavier. But if you put that same grape into really sugary water, which has a low water potential, water gets sucked out of the grape and it starts to shrivel up. Water is just following that downhill slide from high to low potential. And a tree? It's basically a giant continuous version of that exact same experiment. The soil is like the pure water, it's got high water potential. But the dry air, especially on a sunny day, that's like the super sugary water. It has an extremely low water potential. So water just gets pulled all the way up, following that massive gradient from the damp soil to the dry atmosphere. So let's put it all together now. Let's trace the full journey of a single drop of water, from a root deep in the soil all the way up to a cloud in the sky. Okay, here's how it works. Step 1. The sun powers transpiration, which creates this powerful pull, that super low water potential up in the leaves. Step 2. Because water molecules are sticky and they hold on to each other, this pull yanks on the whole column of water on the trunk, like it's one long, unbroken chain. Step 3, that tension pulls water from the roots into the stem. And finally, step 4, this makes the roots draw in brand new water from the soil to replace it. The whole thing is a silent, sun-powered hydraulic system. It's incredible. And here's why this really matters. This isn't just some neat biological trick. Every single tree on Earth is an active biological pump. It's a critical link, constantly moving huge amounts of water from the ground back up into the atmosphere. It directly influences our weather, our rain, and our climate. So that kind of leaves us with one last big thought to chew on. If a single tree is a powerful engine shaping its little corner of the world, what does that make an entire forest? It's not just a collection of trees. It's an engine on a planetary scale, silently shaping the very world we all live in.